Looking at Chapter 18, Problem 18, Parts A, B, and C, we're asked to produce the product from each of these reactions. So let's keep with our general strategy in determining what the major functional group is in the starting material. So we can see that we have a carboxylic acid derivative with an alcohol and an alkyl group. So this is an ester. We're treating the ester with LDA and then ethyl iodide. So let's recall the structure of LDA. So that stands for lithium diisopropyl amide. So you'll have to remember the structure of LDA is this. This is an amine base. So being a base, it's going to abstract an acidic proton. So the acidic proton it's going to go after is the alpha protons of the ester. There's other protons in this molecule, however, they do not have the acidity of the alpha proton. We can think of this as a pKa of approximately 25. The remaining hydrogens in this molecule will have pKa's of around 50. So the lithium diisopropyl amide is going to behave as a base to abstract the acidic proton. This is going to generate an enolate, put our negative charge in on the oxygen, our lithium counterion. So here's our enolate. Our byproduct is going to be diisopropylamine. So keep in mind, the mechanism by which the next step happens is what we've seen before. This is just a standard SN2 reaction. We're going to have the lone pair on oxygen reform the CO double bond. This pi bond is now going to be the nucleophile, and it is going to displace the iodide from the ethyl iodide. So here's our ethyl iodide. Here's our CH2 carbon. We have SN2 displacement. The byproduct of that's going to be lithium iodide, and the major organic product is going to install that ethyl side chain at the alpha carbon. So just for bookkeeping purposes, here's our inorganic product, lithium iodide. So if you notice overall what we've done, we've substituted a hydrogen in the starting material for an ethyl group in the product. And this is called an alkylation. In part B, we're starting with, in this case, a ketone. I haven't drawn in the alpha hydrogen in this case. I'll draw it in now. So ketones have a pKa of approximately 20 to 25. So the ballpark that we want to remember is 20 to 25 for Chapter 18 material. We're treating this ketone with bromine and acetic acid. So this is going to be an acid-catalyzed bromination reaction. We're going to substitute the alpha hydrogen for a bromine. So let's look at how that happens. So we've seen so far, in the presence of a CO double bond, typically the first thing that's going to happen is protonation. So the acetic acid is going to supply a proton. We now have an activated carbonyl. What happens now is generation of the enol. So the enol is actually the neutral species. It does not have charge. And what abstracts this is actually going to be the acetate anion. So this is how this process is acid-catalyzed. We're regenerating the acid catalyst. So here's our neutral enol. Keep in mind, we've seen the mechanism by which this next step is going to occur. We're reforming the CO pi bond. We're breaking the CC pi bond, which is going to act as a nucleophile. The bromine of molecular bromine is an electrophile. We then break the bromine-bromine bond. And we're going to end up with our substitution product with a protonated carbonyl. So at this step, we can just invoke the bromide anion, abstracting that hydrogen, giving oxygen back its lone pair, and our final product is the alpha bromoketone. So again, keep in mind, all we're doing in these reactions is a substitution. We're substituting H for the electrophile, in this case bromine. In part C, we have this difunctional molecule. We have a primary chloride and we have a nitrile. Let's go ahead and draw in the alpha hydrogens of the nitrile. So for the most part, we've seen CO pi bonds basically increase the acidity of alpha hydrogens. It turns out that nitriles do that as well. And we've seen sodium hydride in the context of it being a strong base. So hydride is bearing a lone electron pair. It's negative. The alpha hydrogens here, let's call them a pK in the range of 25 to 30. So the hydride is going to abstract an alpha hydrogen. We're going to deposit the electrons in that bond on the alpha carbon. Sodium is our counterion. Our byproduct in this case is hydrogen gas, so typically you'll see that bubble out of solution. So now we have a nucleophile at the alpha carbon, and we have an electrophile at this terminal carbon here. So we know that typically you've seen this in SN2. This is an internal SN2 if you want to think of it that way. The nucleophile is going to attack the carbon bearing the good leaving group. We displace that leaving group as chloride anion. Our byproduct of that will be sodium chloride, and we're going to end up with a cyclized product. So to keep track of the atoms, let's start numbering here as 1, 2, 3, 4, and 5. We're forming a carbon-carbon bond between 1 and 5, so we need a 5-membered ring. Let's go ahead and draw that in, and carbon 1 is actually going to bear the nitrile. So we're making this cyclic nitrile, and just to show our inorganic byproduct is sodium chloride. So this is the bond we made between 1 and 5.